Apologies, but I won't be able to make it to the breakout room. I'm on holiday at the moment. That's one of the benefits of doing talks electronically, is you can do them from holiday, but of course, one of the unbenefits is that you can do them from holiday too. So today, I'm going to tell you about some recent results of ours on quantum computing with trapped ions, and they're focused around the chip that you see pictured in this diagram. So this is a fairly standard over the last 10 years ion trap chip in one sense, in that there are gold electrodes laid out by photolithography here, and ions are trapped about 50 microns above the surface of these gold electrodes. But it's non-standard in the sense that it has a new feature, which is that there aren't just these electrical wirings by wire bonds coming onto this chip, but also there's optical wiring coming in by a bundle of optical fibers, which actually are coupled into the chip itself, and the light is delivered to the ions by the waveguide from the waveguides in the chip. So why are we doing that? Why do we look to do that with trapped ions? Well, as many of you probably know, trapped ions are a very successful sort of early technology in quantum computing domain. And many of the very nice results that you'll have seen take place in these long strings of ions, which are typically held in fairly large scale ion traps by the standards I'm going to talk to you about today. So the electrode structures are on the millimeter scale. And what that allows you to do is to confine single atoms in ultra high vacuum. So they're very well isolated, but they can be controlled reasonably rapidly by laser fields. And so these have been as one of the benchmark systems, I think, for quantum computing, in particular through work carried out in Innsbruck and in Maryland, where, for instance, quantum simulation experiments have been performed with over 50 qubits, and certain algorithms are performed on system sizes of 20 or so qubits. So this has been a very rich system. It's been very successful, but we have think it has its limitations. And in a certain sense, that comes from the fact you're dealing with a many-body system. This is a 50-ion system, and the connections between these ions are actually the motion of the entire string of ions. So there's some complexity to that doesn't scale terribly well. And so we don't expect, I think, to be able to scale these sort of approaches beyond about 100 ions. Nevertheless, it's the way in which some of the early adopters in terms of startup companies are working. So this is AQT in Austria and IonQ in the US. So how do we go beyond 100? And for quantum computers, what we think we need is sort of systems of up to 1 million qubits. So that's way beyond this value of 100. One of the approaches suggested in the late 1990s, actually by Dave Wineland's group at NIST, was to modularize the system. And one of the ways they suggested to modularize it was an on-chip modularization. There are a couple of different ways to do modular control of ions, but I'm going to exclusively talk about this method. And the basic idea is that instead of having your entire computer sit in a strongly coupled chain of ions where they all are repelling each other, if you like, you learn how to break the ion strings up into smaller units and in order to reconfigure them for each round of gates, if you like, which would be done on neighboring ions in a single unit, you change the potentials of the trap such that you can shuttle ions around this processor. So in a certain sense, you turn your individual atoms into information carriers for communication channels, which you communicate by moving these ions themselves. And there's various groups who've been pursuing that, including my own and my own work at NIST, actually. And actually, Honeywell industrially have started to follow this approach very successfully in the last few years. But one of the reasons why it has been a bit slower to get to sort of the levels that have been worked on in these sort of linear chain experiments is technical complexity. You need you need a trap which can handle many electrodes which are all wired up electrically. But another challenge you can see is the challenge of delivering. In fact, one of the big advantages of this approach is in somehow parallelizing the system. You can do a gate over here simultaneously with a gate somewhere over here. But the challenge technically with that is that you need to deliver light and high precision light to this region here at the same time as you're delivering light to another region over here. And this multiplexing of the light delivery is something that's extremely difficult to do in our standard setups. Why is that? Because our standard setups are ion traps in an ultra high vacuum system. typically with laser beams in a very standard quantum optics approach delivered through free space. And there's a limit to the stress you can put on a researcher in order to align many, many laser beams in free space with very high accuracy in order to do very good quality gates. So that's what I'm going to tell you about today, is how the use of integrated optics allows us to get around some of these challenges. So we're going to think instead of a system in which we have a laser source. The laser source can be going through a fiber splitter and multi-channels of modulation. This I'm not really going to tell you about today. It's all fairly standard optics in fiber. But what I am going to tell you about today is the heart of the apparatus, that these fibers then are brought inside a 4 Kelvin chamber, so down to a cryogenic temperature, where there's this chip which is able to deliver the light to the ions. And this is not something that we initially pioneered. So the first results on doing this sort of thing were performed at MIT and Lincoln Labs and were published in 2016. But they faced a significant challenge, which was that they actually had free space light, which was then coupled into waveguide structures inside the vacuum system. And they had rather large losses of the light going from the delivered light through to the actual ion itself. So this challenge, in this work here, they actually delivered light to strontium ions at 670 nanometers. More recently, and actually coincident with our recent work, this same group actually were able to deliver all the colors of light they need to individual ions, but with the same challenge of having very high losses in the path from the initial sources, if you like, through to the ion. And what that does is it stopped these efforts from being able to do 2 qubit gates, which require rather higher powers than we need for single qubit gates. So I'm going to tell you about how we do 2 qubit gates in our integrated photonic setup. So what we work with is a trap that looks that's built up in microfabrication, if you like, with a structure something like this. And let me explain to you this structure a little bit. So it's built on a silicon wafer, so you can see that there is silicon down at the bottom here. But on top of that, and primarily the structures we realize are all realized in silicon dioxide with other materials embedded, right? So one set of layers is this light delivery layer, which is done in silicon nitride, which has a higher refractive index than the silicon dioxide, and so is good for light guiding. We then, the light comes in here, it gets diffracted by a grating, and I'll show you some of these gratings in a moment. And it gets diffracted out, and the ion sits about 50 microns above the surface. But you can see the depth of this structure is about 10 microns in total. And then to actually do the trapping of the ions, we need electrodes, right? So we're applying RF and DC potentials to these electrodes. But we also need to protect, if you like, the lossy nature of the silicon from the RF voltages that we're applying on these top electrodes. So throughout the trap, you typically find that there's a platinum ground plane, though with gaps where we need to extract the light because the platinum wouldn't allow light to pass through. So how do we do this complex stack up? We don't do it ourselves, but we use a commercial foundry in the Netherlands called Gratings. And you'll see here, what you get is, if you like, you can put a bunch of different designs on a single wafer run. And indeed, all of these are different trap designs, which either are testing the integrated optics or have different patterns of delivery of light for controlling ions. Now, one of the special things that Gratings can do is this multi-layer of silicon nitride. And the way we use that, it's got a very nice feature, which is in a thick silicon nitride layer, then what happens is the optical mode is extremely well confined. And this is good because you can make a waveguide bend a lot, as it would be in an optical fiber. If the mode is very well confined in the core, then you can put in bends with low loss. But it's not so good if you want to match the light here to the mode of a single mode fiber, which is a few microns in size. So actually that's the key in this second layer introduced by Gratings, is that uses a very thin layer of silicon nitride. And that means the mode is much larger and means it matches a fiber mode much better than we had before. So in fact, what we can do there is that we can use thicker layer for routing, but we can actually butt couple a fiber right up to the edge of the chip and couple with a sort of 1.5 dB loss into these waveguides here. And then an adiabatic taper actually takes the light between this type of mode and this highly confined mode. So the other component of the integrated optics then is these gratings, right? So these really are diffraction gratings sitting in the waveguide. They look something like this. So here you see the waveguide coming in as a fairly narrow waveguide. We then have an adiabatic tapering so that the wave, the optical wave, if you like, expands laterally, not in the vertical direction, until it comes to this grating here, which you'll see is curved, which allows us to generate or design the wave or the emission which will come from this curved grating. Yeah. And the curviness of this nature is because it's focusing to the position of the ion. And in the particular chip shown here, here's just the beam profiles that we can measure with a microscope, if you like. We see that we get a focus which is roughly 6.5 times 3.7 microns. And here in blue, I've plotted where the ions would sit in the focal plane, which is 50 microns above the chip. So this is the chip that we made and that we've got results from, if you like. Here you actually see the 8 fibers coming into this structure. So this is the optical delivery. Here you see where the wire bonds are, which are doing the electrical delivery. And there are 3 little zones in here, which if I zoom in on them, you'll see both of them have 2 gratings, one actually for 866 and 854 nanometers, and one for 729 nanometers. And 3 of them are identical in this case. Yeah. So how well does it work? Well, we have a special coupling setup that we had here, which, as I said, was able to get to a sort of 1.5 dB loss. And what that allowed us to do was actually demonstrate fast Rabi oscillations in a few microseconds using the waveguide delivered light. But this was really a signature to us, which we were happy about, which was that we could get in a regime of fast, high enough power delivery that we could do multi-qubit gates, which use the power less efficiently. So actually here is a fairly standard trace that you would have in trapped ion physics. This is populations of 2 ions now, and they start both in the, sorry, I can't see it for the zoom, but I think they start in the up state, okay? And what you see is a Rabi oscillation of sorts, but with this extra kink in the middle. And actually at the point of this kink, what you see is that the population is all either up, or down. And that's actually the time of a 2-qubit gate that creates maximally entangled state. And it does it in around 65 microseconds. That's a fairly standard time in our laboratory. And then we can evaluate the fidelity essentially by doing an interference experiment involving this phase between the 2 components of the entangled state. And what you should observe here is that the contrast of this oscillation is very good. Yeah. And that indicates to us, or lower bounds of fidelity, which we can calculate to be 99.3%, which is not so far off the best gates that have been performed in trapped ions, and is actually among the best gates that we've performed in my laboratory. So what that shows to us, if you like, is that the integrated optics as an approach, straight out of the box, if you like, was able to produce as high quality operations as that we could do with our standard free space delivered optics. We understand the errors well. We can account for pretty much all of the errors that we have. And I should just point out that actually in a certain sense, the trapping in this chip is not terribly well behaved. So many of these error sources are rather large, even just because of the way the trap works. It's not terribly well behaved. And we also didn't yet do gates in a way to sort of protect against any of these components here. So in a certain sense, mitigation techniques are known for many of these sources of error. So where can we go from here? We can perform high quality 2-qubit gates, but it's not just that we would like to use these standing waves for. So these optical delivery for. So here's another type of chip, which takes us into a new domain for us in trapped ion physics, because here actually we're splitting up light on chip such that we have 2 gratings which are facing each other. And what that means is we can generate standing waves at the focal plane of the ions, or at least standing waves in one of the directions. It's a traveling wave out of the chip, but a standing wave parallel to the chip. And that's nice for us in the sense of doing 2-qubit gates, because in our standard gates, if you like, we have a traveling wave. And what that means is we always have some strong off-resonant processes due to driving the spin flip transition off-resonantly. Yeah. Whereas in the standing wave, we can control where we sit in the standing wave. And what that means is we can control whether we're experiencing electric field gradients or we're experiencing the amplitude of the electric field. And so by tuning the position of an ion in this standing wave, we can vary the the strength with which we drive directly the transition. Now, why am I interested in gradients versus the strength of the field? Because if I have a transition that's driven strongly in the electric field, it's the gradient of the electric field that means I can drive a 2-qubit gate. Okay, so the two things are two elements that I care about. If I want a good 2-qubit gate, I want a strong gradient there and no intensity. So here's some results from the latest chip that we've stuck in, which has a standing wave. Here's an ion being translated in position, and at every position we perform Rabi oscillations. And you can see that we get variation between places where the Rabi oscillations are fast, and if I look at a time trace going across here where it's much slower. So we can plot these out. Here we're driving a quadrupole transition in the calcium ion. So actually the places where the strongest driving is different for the various different transitions we have in our quadrupole transition. Yeah. So we can choose then to work with, say, a particular transition, the delta MJ equals 0. We would choose, if we want to do carrier oscillations, we would choose to sit here where we get spectator transitions nulling out to 0. But if we wanted to do gates on that same transition, we'd probably go and sit at this point here, where sidebands would be strongly driven, but the carrier would not be strongly driven. Yeah. At the same time, we can choose also what our AC start shift should be, that we can either go and sit at a point where there is very small AC start shifts because the intensity of the light is not high, or we can go and sit at a point where the AC start shifts are large. So what else can we do with this? Well, we can think about scaling further. One of the things that I didn't show you in this picture up here was this cross region. And what is it? It's what we would call a junction. So that's very non-standard in ion trap physics. A few of them have been demonstrated, but not at any length. So actually one of our waveguide chips, and here you see in red the waveguides coming in, this is really a design picture rather than the actual chip, is something which has one of these crosses. And it also has this zone here, which you'll see many optical lines coming into. Actually, that's a region where we have 5 couplers that are aiming to address individually 5 different ions. And if we look at the optical mode there, then we can also see that we get 5 different beams, all individually focused to a sort of 1 or 2 micron spot. So the next generation also has to think a bit further. One of the challenges we have in today's traps is actually that we see that the ground plane is not good enough. And it also, we see that when we pulse light through these gratings, we see that the ion feels the effect of electric fields, which we think is something about generating photoelectrons in the silicon dioxide. So it's something that we'd like to get rid of. For that reason, in our next generation, we'll have a transparent conducting coating on the top of the chips. And we think about changing our material here of the conductor in order to get better conductance. The other thing we'd like to do is to get all of the wavelengths we need onto the same chip. So there we've now integrate alumina waveguides on the same chips. So I've said a lot about radio frequency traps there and the delivery of optics. The other thing that we've been thinking hard in my group is about the challenges of overcoming the challenges that radio frequency traps involve. And there are various things, and you can kind of see them in these linear chains here. A single RF null is kind of an intrinsically 1D thing. That comes from Laplace's equation, actually. And here, what you see in these junctions is we'd like to move into 2D. And actually overcoming the fact that you have to sit in a region with high RF is one of the challenges of working with these junctions. There's a problem here on the microscopic scale, which we deal with daily, which is to co-align the radio frequency pseudo-potential that we have with static potentials. We call that micromotion compensation, but it forms a daily part of our task. And the other thing in RF traps is that you have to put high voltage radio frequencies, so 100 volts or so, onto these chips, and the chips get hot. And that's going to be a challenge as we start to scale up. So one of the things we're now investigating in my group is now an alternative approach, and that's to replace, if you like, the RF potential with a homogeneous magnetic field. It has to be a large magnetic field of several Tesla to realize penning traps. And the new thing we'd like to do is realize penning traps which are small, i.e. that the electric potential for each ion is separate to each other, but that the ions still interact via the Coulomb interaction, which we use for performing gates, by the fact that these two traps are close together. So we can reflect on how that compares to work in RF traps. One of the great advantages is that the static potentials you can make, which are required for the penning trap, are much stronger than you can get for RF traps. And so it allows us to think of things where the distances between the ions are not so large compared to the height, are small, if you like, compared to the height from the electrode plane. So we've sort of mapped out how we might get with 300 volts beryllium ions on a large lattice, if you like. We say infinite, that's just to ease the calculations, with decent Coulomb couplings between the ions. And so somehow already we see the perspective that here we could potentially make chips with this sort of density that could trap large numbers of ions. I say could because, of course, we haven't done it and this is a long way from doing. But one of the great advantages being there's no RF dissipation there. The other great advantage is that in these 2D regions where previously we have this large driven RF motion, the nice thing about the penning trap is that the magnetic field is completely homogeneous and provided by an external magnet in a certain sense. So now transport of ions can be taken away from being along 1D channels and then in 2D at special regions where they have to be in very non-ideal conditions. And we can transport these potentials by moving quasi-static voltages in multiple dimensions, if you like. Yeah. So we feel positive that that's got a good perspective for scaling. So with that, then I come to the end of my talk. So in summary, I've told you about the use of integrated optics for doing quantum gates, and in particular that we've been able to reduce losses from a level of sort of 33 dB or so down to sort of 6 to 7 dB, which allows us to deliver enough optical power to do multi-qubit gates. And that's a big step forward because that allows us to do all the things we need to do, or it gives us the amount of power to do everything you need to do for quantum computing, if you like, on chip. And furthermore, I told you a little bit about these micro penning traps, which may allow us in trapped ions to scale to 2D in a facilitated fashion. That's something that we start to build experiments for today, supported by the ERC. And we have not just designs now, but things coming back from the workshop to try and potentially load these setups in the fall. So with that, I'd like to thank you for your attention. I thank the team at ETH who's involved in this. In particular, these people were involved in the waveguide stuff, I think led by Karan Mehta, who brought this technology to us from MIT. And on the other hand, the penning traps where Shreyans, Tobias, and Pavel are really the team building up this penning trap setup. So with that, I thank you again for your attention, and I look forward to any questions that you might have.
Thank you, Jonathan, for this very interesting talk. And while we are still waiting for some questions in the Slack channel, I wanted to ask you, so how many qubit gates have you already performed on the chip? You mentioned there are 8 fibers, so I would assume like 4 gates?
No, okay, so that's, I can clarify that. So at the moment, the experiments I just explained to you are taking place in one region, yeah? So there we can do 2 qubit gates in this one place, if you like. But of course, we can do sequences of gates. So we've recently been doing experiments which I guess have the equivalent of 32 gates in a row. We have a bit of a problem on that chip because the ions heat up rather fast. So the gates quality is not staying the same as a function of time at the moment. But that's something that we think we can mitigate with, particularly we worry about these insulating layers which are exposed to the ion at the moment. And we think we can mitigate that in the next round of chips through the use of conductive coatings.
Okay, thank you. So we have here some questions. How would the 2 qubit gates work in the penning trap approach? Doesn't the always on coupling make them more complicated?
Good, I'm glad you asked. I just explained that probably too quickly. So the coupling that I'm talking about here is essentially the fact that you've got at these 2 individual sites, you've got an oscillator. And these 2 oscillators, when they oscillate, they're coupled oscillators by the Coulomb interaction. Yeah. So at this particular distance for 2 megahertz oscillators, what you get is that there's 2 normal modes of this system where the ions, if you like, are in either a stretch mode or a common mode of motion. They either oscillate together or out of phase. And that's split by this 55 kilohertz. So if it was one was to do a quantum gate on those 2 ions, you would be doing it on the spins, and you would probably put your laser somewhere halfway between these 2 modes. and you would get a gate, I guess, in around 50 microseconds in this particular case. Yeah. So the gates would be exactly the same sort of gates I'm telling you about before. In the previous case, we had ions which are separated by 5 microns, so they were much closer together. And this exchange interaction would have looked much larger, if you like, but it's the same basic gate. You drive with the lasers, there's motion transiently, and you get a gate after a certain amount of time.
Okay, thank you. And another question, what part of the fabrication is standard for ionics and what is custom?
Yeah, I think for them, they're specialists in doing photonic chips. So actually the layers that I told you about, which was one of the nice features that we like, sorry, I go back to, let me find the Linux bit, is this ability to do these multiple layers of silicon nitride. I think actually that's their standard thing, but maybe the thing they also flag, because this allows, for instance, good coupling onto the chip. The thing that's less standard for them is putting the metallization layers on the top, right? And in particular, I think initially platinum was an easy thing for them to do. It's got a higher resistance than we'd like. And so in recent rounds, we've been experimenting with them or asking them to do other materials and to test their fabrication with other materials. So I rather think for them, they're a photonics type foundry. So the photonics is easy, but maybe the electrode stuff is different. I wouldn't say it's harder, but it's different for them to do. It's non-standard.
Good, then we don't have any more questions. I want to thank you, Jonathan. And for more deeper discussions, don't forget to join the roundtables at the end of the session.
And just to remind you, then I can't join the roundtable because I'm on holiday, but if you have questions, please feel free to email me and send them through.